Hello, so you're welcome to our, if you like, our last lecture on techniques of integration, if you like, on these topics. In our last video, we covered integrals of rational functions and as well as how to establish the reduction formula for integrals. Okay, so for the reduction formula, you can try these exercises. If you don't have any exercises, you can try to establish that cosine to the n x dx is equal to this formula. Hence, you can show this. You could also try to use integration by parts to establish these ones. So you can try these and see if you can establish them. Okay. In today's lecture, we want to look at improper integrals. So what I would do is I would give me a minute here, setting my my distance. So we want to look at improper integrals. So far, we've been looking at, if you like, proper or normal integrals. In the next couple of slides, we want to talk about improper integrals. So what are improper integrals? Now, if you recall, we defined a definite integral to be this. If this is not a full definition, if f is a continuous function defined on a closed interval like this, then what we did was, divide the interval into sub-intervals of equal width such that the integral from a to b of f of x dx is equal to the limit of this thing here, this expression. Okay, and so note that in this definite integral definition of that, you need f to be continuous, as well as the fact that the interval here is finite, you see, from a to b, where a and b are known. Okay, so the question we want to ask is that what happens if, for instance, this function here, f of x here, is discontinuous at some point in this interval a to b? Can we still compute the so-called area under the graph of f if that happens? Secondly, what happens if the domain of f is infinite or semi-infinite? All right. What if a is going to negative infinity or is negative infinity? What if b is positive infinity? What if this is a number and that is infinity? What do you do in those instances? So when that happens, we get what is called an improper integral. Okay, so we'll take a look at this. So these diagrams illustrate what I mean by that. So in A, I have a function f of x, which I sketched here. 5 ln x all over x cubed is something like this. Here, the limit is from 1, but this is going to infinity. We are not stopping at any point. All right, so the question is, if I want to integrate from 1 to infinity of this function here, can I do that? And how do I do that? Okay, what about this one? In this case, the limit is finite, if you like, for the interval. I want to integrate from 0 to 4 of 1 over 5x, this guy here, all right? But in this case, what you notice is that as you approach 0, this function goes to infinity, okay? So at this point here, in the this lower limit here, the function goes to infinity. So again, in that case, how do you find the limit of this? How do you find the integral for such a problem? Or suppose you want to integrate from negative infinity to infinity of this, what happens? So these types of integrals where the limits are either infinity or the function, the integrand itself, right, is discontinuous at some point within the interval are known as improper integrals. So they are integrals with infinite intervals of integration or unbounded integrands. Okay. Now we want to study these because they are important. You come across them in different types of applications. So that's why we want to learn how to do that. Okay. So we'll first take a look at the first set of improper integrals, things that look like this. And then once we are done with that, we'll come to the case where you have unbounded integrals like these guys. Okay. So here is a definition So that will help us, to be able to perform improper integrals. All right, we already know how to perform definite integrals. And so this definition helps us to translate from improper, if you like, to a proper integral, and then find a limit. Okay, so um, the first point of this definition says if f is continuous on a to infinity, then the integral from a to infinity. Now, in order to avoid dealing with the infinity up here, you replace the infinity with some number. All right, find the integral of this, and then find the limit as b goes to infinity. Okay, that is the point here. So provided this limit exists, then you get a finite number, which you represent, if you like, the area under the graph. This is a similar one. In this case, we are moving from negative infinity to a point B and want to integrate this. So again, replace the negative infinity by some number. In this case, I call it A. And then what you do is that you evaluate this definite integral now. And then once you are done with that, you find a limit as a goes to negative infinity. Okay? So anytime you have infinity in any of these limits, this is the approach you have to take. Thirdly, well, before I go to the third one, remember that if these are convergent, right? If the integrals are convergent, if the limit gives you a finite number or value, then this integral is convergent. If it doesn't converge to a finite number, it goes to infinity or negative infinity, then it is divergent. Okay, so each of the improper integrals is convergent if the limit exists and divergent if the limit does not exist. The third point in the definition is that if f is continuous on negative infinity to infinity, then what you do is that you split the interval into two. So from negative infinity to infinity of f of x dx should be equal to the integral from minus infinity to some number c. Okay, the choice of c is not that important. F of x dx plus the integral from c to infinity of f of x dx. Well, we've already seen how we deal with these cases. So you can then go ahead and use the previous points definitions to do this, and then also do this. Now, if both of these, so this is very important, both of these integrals on the right-hand side have to be convergent for this integral to be convergent, all right? If any one of them is divergent, then the whole integral is divergent. So if I compute this first one on the right-hand side and is divergent, I don't need to do this one. I can just conclude that the integral is divergent. Okay, so that's the first definition that we want to deal with. We'll do a couple of examples of this, and then we'll move on to another set of improper integrals where the function f is unbounded within the limit. Okay, so here's a simple example. We want to find the integral from 1 to infinity of 1 over x squared dx. Okay, so once again, because we have infinity here, replace this with some number. You can call it b or t or whatever. So in this case, I replace it with t, and I'm finding the limit as t goes to infinity of this integral. So I just compute this with all the knowledge we know about computing definite integrals. Once I'm done with that, I find the limit as t goes to infinity. And so this is x to the negative 2. I can integrate that to get negative 1 over x. From 1 to t, I plug in my t and my 1, and I end up with this expression here. Once I'm here, I can find the limit as t goes to infinity. As t goes to infinity, this expression goes to 0, so I'm left with 1. And so this integral gives me 1, which implies that the improper integral is convergent, and it converges to the number 1. Okay? Okay, so that's how you do that. We'll look at a couple more examples. This says determine if the following integral is convergent or divergent. If it is convergent, then find its value. Okay, this is similar to what we did before. We'll take a look at it. This is another one. So let's start with A. I want to integrate from 1 to infinity of this. So once again, replace the infinity with some number, some variable, I should say t. Find the limit as t goes to infinity of 1 to t of 1 over x. If you integrate 1 over x, it's just ln x, right? So this is limit as t goes to infinity of ln x 1 to t. If you plug in your limits, you end up with this expression. Okay, ln 1 is 0. So this guy goes to 0. That's fine. But the limit as t goes to infinity of ln t, if you remember the graph of ln, it keeps going like this, right? And so as t goes to infinity, ln t goes to infinity, which implies that this integral is divergent. Okay? Is divergent. So you can find a number direct, a number representing the area, if you like. Okay. B, we want to integrate from negative infinity to 0 of 1 over the square root of 3 minus x. Okay. What you should note is that this, the integrand, this expression, this function 1 over root 3 minus x, this integrand is continuous within this interval. So that is important to take note of. It's the same thing with A as well. Okay. So once again, I replace negative infinity with a variable. I call it t. So I have a limit as t goes to infinity of this expression. This I can write as 3 minus x to the negative half. All right. So I can easily integrate this. I add a 1 here and divide by that. If we integrate what is in here, you get negative 1. So there's a negative 2, the square root of 3 minus x, integrating from t to 0. So plug in 0 and plug in t, and you end up with this. Okay? So I have a limit as t goes to negative infinity of this expression. Okay. So what happens? As t goes to infinity, all right, of course, this becomes t goes to negative infinity, all right? This is a negative big number, so this becomes positive, but positively big, right? This is massive. So which means that I'm going to have something like negative 2 root 3 plus positive infinity, if you like, and this is just infinity. So as t goes to negative infinity, this expression goes to infinity, which means that the limit is infinite, and hence the integral is divergent. Okay? So both of these integrals are divergent from what we just did. Good. C says we want to integrate from negative infinity to infinity, all right, of x e to the negative x squared dx, all right? So the easiest point to split it is that you can split it in the middle from negative infinity to 0, and then integrate from 0 to infinity. And then we solve this, the first expression, integral on the right-hand side first. Once we are done, we'll come out, we'll do this one. In fact, you can, if you are careful, you will notice that this is symmetric, right? This is the same expression here. One is from negative infinity to 0, the other is 0 to infinity. So once you get this, it's easy to pull out this. If this is positive, this will be like a negative of it. Okay, in any case, let's do this one. I call it I1, which is negative infinity to 0 of x e to the negative x squared dx. Okay, so what do we get here? So again, I replace this with a t. So I'm going to have a limit as t goes to negative infinity of this expression here. Here, I haven't gone through all the details of how you integrate this, but we have learned different techniques of integration. You can use the method of substitution. Substitute for negative x squared or just x squared. If you substitute for that, then you can easily integrate this guy. When you integrate it, you're going to have negative 1 over 2 e to the minus x squared, and the limits are from t to 0. Plug in the limits. When x is 0, you're going to have negative 1 over 2 plus when x is t, you get this guy. Okay? And you take the limit as t goes to negative infinity. Note that as t goes to negative infinity, this goes to 0, right? The e to the negative t squared goes to 0. And so you are left with negative 1 over 2. All right? So we have this, the first expression on the right. The next is to do this one, following a very, very similar approach. Okay, so if you do a similar thing, in this case, I replace the infinity here with a t, and then integrate again, use the method of substitution, and you end up with this. Plug in t, and you have this expression. As t goes to infinity, the first term here goes to 0, and you have 1 over 2. Okay, so you added two expressions. In the first case, we got negative 1 over 2. In this case, we have positive 1 over 2. When you add them, you get 0. Hence, I'm recording a video. Hence, the improper integral is convergent and converges to 0. Okay, sorry for the interruption. Okay, so Why is it 0? Now, if you plot this expression here, then you see why the integral goes to 0. So this is the expression from negative infinity to infinity. The function is x e to the negative x squared. So when you integrate from negative infinity to 0, you're going to get something that is negative here, right? And then if you integrate from 0 to infinity, you're going to get a positive quantity, but they are the same, right? One is just the flip of the other one. So when you add a negative and a positive, that's how you get 0. Okay. Okay. So that was the C. In the D, the last example we want to solve in this, we want to integrate from -2 to infinity of sine x dx. This is equal to the limit as t goes to infinity, right? I'm replacing this with t of this. The integral of sine x is just negative cos x, so you have this. So you plug in t and -2 and you get that, right? Okay. Now, so here you see that as t goes to infinity, as t is increasing, the sine function is oscillating between -1 and 1, right? It is oscillating. It's not convergent to a number. So because of this, because of the cos of t, this integral is not convergent. It is divergent, all right? Because of the cosine of t, because it's oscillating between -1 and 1. All right? Good. So so we've done examples for these ones. You can try these three. They are very similar to what we've done. In these cases, the function here, the integrand is continuous in the interval in all of these, and the ones we've done as well. So we want to look at a second set of improper integrals, in which case the integrand here is discontinuous. All right, those are the most, if you like, the most dangerous ones that you have to be careful about. All right, if you're not careful, you'll miss them and you get a wrong answer. I will show you an example of what I mean. All right, so let's look at improper integrals with discontinuous integrands. Here's a definition and how you solve that. If f is continuous on A to B, all right, this is open, okay, but is discontinuous at B, at this point, at this endpoint here. If the function f is discontinuous at this point, then what you do is this. You do something similar to what we've done before. The interval is from A to B, all right? So replace is discontinuous at B, so replace B with some variable, call it t, and then you find a limit as you approach B from the left-hand side, okay? As you approach it on this side. This is fine, A is okay. B, the function is discontinuous there, so replace it with some variable and then approach B, okay? So A to B, f of x dx is the limit as B, so I replace B with a t. So I want to find the limit as t approaches B from the left-hand side, okay? Of A to t, f of x dx. So again, what I do is that I try to solve, all right, integrate this, and then after that, I find a limit as t approaches B from the left, okay? If the limit exists, of course, then the integral is convergent, otherwise it's divergent. Okay, so this is a similar one. In this case, it's A to B. It is discontinuous at A, all right? At A is discontinuous there. So you do a similar thing. Because it's discontinuous as A, you replace A with a variable and then you approach A from the right-hand side, okay? From this side, my right. Okay, so in that case, you write, let's replace A with a t and find a limit as t approaches A from the right of this integral. Once again, if it's convergent, if the limit exists, then the integral is convergent. Then finally, if f has a discontinuity at a number c in the open interval this. So there is some number within the interval a to b, somewhere in between within that interval where the function is discontinuous, f is discontinuous. If that happens, what you do is that you split it in two, from a to a number called that number c, and then c to b, and then you deal with them separately, okay? then what you do is that you write this as integral from a to c, where c is the point of discontinuity, plus c to b. All right? We've already seen in the definition A and B, we know how to deal with this case. We also know how to deal with that case. So we deal with them separately. Once again, if both of these integrals converge, then the total integral here, this improper integral converges, and then you can add the two of them to get that. If one of them is divergent, then the whole improper integral is divergent. Okay? So that is how you deal with these cases. Once again, these are more serious. So whenever you get an integral, whether you know it's proper or improper, make sure that the function here, this function here, is continuous in the interval a to b before you start solving it. If at any point it is discontinuous, then you have to use these methods in order to try to solve it or find out whether it's convergent or divergent. Okay, so take note of that. Let's do this example. We want to evaluate this from 0 to 3 of 1 over the square root of 3 minus x. Okay. Now, in this case, if you're not careful, you have to be careful, right? Don't just go straight away to solve it. Note that when 0 is fine, but when x is 3, this function f of x here is discontinuous. You have 1 over 3 minus 3 is 0, right? So you have 1 over 0, that's infinity. So it's blowing up. This function blows up at 3. That is why this is an improper integral. So in that case, you have to replace this 3 with some variable and find a limit as you approach it. Okay? So note that the integrand has an infinite discontinuity at x equals 3. All right? Actually, I have a figure here. Let me just show it quickly, and I'll come back here. So here, this is the function we are dealing with. From 0, it is fine, 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 fine. But when you are getting close to 3, it goes zoop to infinity. See, it goes to infinity at 3. So it's discontinuous here. That is why you have to be careful with it. Okay, so let's come back here. So when that happens, I need to replace the 3 with a t and find the limit as t approaches 3 from the left, right? We're approaching here from the left. Okay. So now I just integrate whatever is here and then find the limit. Okay, when I integrate this, I'm going to get that. This is just 3 minus x raised to the power negative half. We've seen that before. So you just integrate it and you get this. Plug in t and 0. If you do that, you're going to get this. Okay? And find the limit as t approaches 3. As t approaches 3, this first term here goes to 0, right? This goes to 0. So you have 0 plus this. And so you are left with 2 root 3. So if you evaluate this, you're going to get 2 root 3. Okay, good. Now, in the next one we want to look at, well, let's go to it. I'll come back to the figures. We want to solve this example now. This is the integral from 0 to 3 of 1 over x minus 1 dx. Okay, so it says evaluate this if possible. Once again, if you're not careful and just go ahead to integrate it, you're going to get a wrong answer, and I'll prove that to you. So why is this an improper integral? It is improper because at x is equal to 1, this function here, our f of x, 1 over x minus 1, blows up. It goes to infinity, all right, at x equals 1. And 1 lies in this interval. You see, this is from 0 to 3. 1 lies in that interval. And at 1, this guy goes to infinity. Okay, so that is why this thing is an improper integral. If I go back to the figures, this is how it looks like. If you plot it, you will see that there is a vertical asymptote at 1. Okay, at 1, you have a vertical asymptote. So for x greater than 1 is fine. You get this function. For x less than 1, you have this guy here. Okay, from 0 to 1, it's fine. But at 1, and we need to integrate from 0 to 3, all right? So something in between 0 to 3, there is a 1 where the function blows up. So that is why you have to be careful with it, okay? So let's see, how do we do that? So you have to, because there's a blow up at x equals 1, what you do is that you have to split the integral from 0 to 1 and then from 1 to 3. If there are several points where it blows up, you do the same thing. You split it into this individual ones. So, so let I be equal to now integral from 0 to 1, because it's a blow up 1 over x minus 1 dx, plus from 1 to 3 of the function. Okay. Now we know how to deal with these ones. So I'm going to replace, we're going to do this first, and then we'll do this one. So for this first case, I replace 1 with a variable called t, and integrate this, and then find the limit as t approaches 1 from the left. Okay. When you do that, now the integral of this is just ln x minus 1 from 0 to 1. Let's go to the next. So I'm going to have a limit as t approaches 1 of this. All right. Know that ln of absolute value of -1 is just 1. Ln of 1 is 0. So this goes to 0. So I just have ln of 1 minus t. Well, it's the absolute value of t minus 1. So I can put 1 minus t as well. Okay. And remove the absolute value, because I'm approaching, remember, it's 0 to 1, and I'm approaching 1 from the left hand side. Okay, so whatever is there is less than 1, so it's positive. That's why I can remove the absolute values. Okay, now if I approach 1, this guy is going to 0. Remember the ln curve. As you are approaching 0, ln is going to negative infinity. So as t approaches 1, this guy is going to 0, and ln of 0 is approaching negative infinity. All right? There is no value for ln 0. Okay? As you're approaching 0, ln goes to negative infinity. So we get negative infinity here. Okay? Remember that there were two integrals, this and this. But we've just seen that the first one is divergent, is going to negative infinity. So we really don't need to even evaluate this. We don't need to do it. Okay, so this is divergent. Hence, the whole integral I is also divergent. And so we don't need to evaluate the second expression there, the second integral. We can just conclude that the integral is divergent. Okay, so once again, these types of integrals are very tricky. And so you have to be very careful when you are solving any integral at all. Make sure that the function is continuous within the interval that is given to you. Okay, so here is a warning of what I've been saying all along. So if we had not noticed that there is a discontinuity at x equals 1, okay, and then we just went ahead to integrate it, this is what we are going to get. You're going to get, if you do this, you're going to get ln, right, of x minus 1 from 0 to 3. You plug in your 3 and you get ln 2, minus plug in the 0, you have ln of 1. Well, ln 1 is 0, so your answer becomes ln 2. But that ln 2, even though it looks nice and is neat, is a wrong answer. It is wrong because the function here is discontinuous at 1. And so this is a wrong answer. Okay? So it is always important, very important, to always check whether a given integral is an ordinary one, or if you like, a proper one, or it is an improper integral by looking at the integrand, the function f, on the interval to see whether it is continuous or discontinuous. All right, so be very careful with that. That is, so that will bring us to the end of improper integrals. These are some exercises you can try your hands on. This says which of the following integrals is improper and why. In fact, this question, you should always ask this question before you evaluate any integral, any definite integral, well, definite or improper. Whenever you're giving integral, try to answer this. Check whether it's improper or it's not before you go ahead to apply all your techniques, okay? And this is determine whether the integral converges or diverges, and if it converges, find its value, all right? So again, try these ones. If you have problems, you can let me know, okay? So all the best. We are done with techniques of integration, improper, trigonometric, hyperbolic integrations. We are done with all of those. The next thing I would probably cover is applications of integration, right? Revolution, the volume of objects, volumes of if you revolve a function around some axis, you get some volume that you can determine. Okay, so we'll deal with that later on. I'll cover that later on. Okay, so all the best.